Okay, fantastic. So week 2, and we will address basics of heat transfers. How do we transfer heat? How do we lose heat? It's very important for us to understand these concepts. Probably the layman person understand them by just observing. Things you always lose heat, you always gain heat, and you always feel comfortable, and probably it's something you deal with every day. So we'll talk a little bit about the science behind that, and I will also talk about insulation. Everybody is telling you about weatherization and insulation, and I want to show you mathematically how there's a limit to insulation. It's not always the cure-all. Okay? So heat transfer modes and their functions. Heat transfer fluids used in HVAC. What kind of heat transfer fluids do we have? So to move the heat from the boiler over here all the way to the room, how are we going to do that?
Water.
Can you water? What else? Steam. You can use warm air. Excellent. And sometimes you can use glycol for hot water system if you want to freeze. So there are some differences between those fluids, advantages and disadvantages. We'll touch base on the science behind it, but I'm not going to go too deep. Location of heat losses in a building. Where would you lose most of the heat? Probably not the best time to have you think about that because you are facing it. Probably if you go with a thermal camera, you can touch the walls and spots, you can see the heat. Recognize heat transmission requirement. How do we transmit heat from one place to another? Well, demonstrate heat loss through a wall calculation. We did that last semester. I'll go over it again. Just as a reminder, because next week we'll do what? A heat loss for a house. Okay, let's start. So, 3 ways to transfer heat is conduction, and radiation. What is conduction? Solid to solid. So me touching the table here, that is conduction through the table. Has to be solid. Convection is through fluid, and that fluid could be either gas or liquid, and it could be also forced or natural. Natural is when we use buoyancy. The basic idea that the fluid, when it gets hot, it expands. It's less dense, so it dries out. So eventually it cools out and comes back again. And usually you have that lava lamp, you turn it down so you can see the convection going up and down. You just keep going over and over. It's natural, it's free, gravity is cheap, it's reliable, it's always the same. And then radiation. Another way to conduct heat. What is a big example of radiation heat? Radiation heat, huh? Yeah, that's the biggest, simplest example. The sun is radiating here. Is there any medium between us and the sun? No, there's vacuum. There's nothing. No air, no solid, nothing. It's basically radiation. It takes the radiation to come from the sun to the earth, 8 minutes. And it's just rays. So that's fast. Heat lamps. When you cook, you go to fast food restaurants, they always put the food in heat lamps. Why? Yeah, but how come not hot air?
Because it'll dry it out.
Yeah, you want to heat the food, not the air. So that's another thing to think about. There are some companies that sell you kind of light fixtures that heat the space. It does not heat the air, it heats only the objects, whatever it hits, cannot light. So see how we are lit now? Same thing, the heat will hit us, and the air will be not an object. That's usually great for big warehouses, garages, where you don't want to heat the air. It's going to be a lot of fluid to heat. So it will save a lot of energy. Actually, we had a previous student who graduated from this program 4 years ago, who has his own company now that he makes those radiators.
How many years ago?
4 years ago, before I was born. He was one of the first people to graduate. He comes here usually and gives a lecture, and I have his presentation. He has a company in Worcester, and actually he offered to put his radiators in the shop. But I don't know, some technicality didn't work. But it's a good idea. Keep it in mind, if you have a big space to heat, maybe it's better for you to use infrared heaters or light, heat lamps. Usually when you go to a restaurant or so forth, you will see those heat lamps. You don't see, because you're outdoors, they're not gonna put something that blow hot air, you just look really wasteful. These are much better. Okay, why do you need to know these modes? Conserve energy, limit heat loss, transfer heat from one location to another, also heat distribution. What do we say the best character of the system you put in? If you want to put the best system, what will be the characteristic of it? Huh? Efficiency. You don't want to hear it or feel it. It's quiet and good distribution. You don't want to have a cold spot and hot spot. You don't want to go to the bathroom and then go outside the bathroom. It's kind of difference of temperature. You should not feel or know or sense that it's available. That's the best system ever. So we will strive to that, depending what budget we have. So heat transfer fluids, they are used for convection. The said fluid is convection, either forced or free. How do we do forced convection for water or liquid? Pumps. We have to use a pump. If it's air, we have to use a fan, inducer fan. What if it's steam? How do you move steam?
It moves itself, doesn't it?
Yeah, pressurize it. You heat it more, it moves by itself. Steam has its own moving power, mechanically strong, does a lot of things. Great source of energy. Okay, air, water, sometimes we have glycol or different mix. This is preferred in some systems, especially in places where it gets really cold, because it doesn't freeze. It's basically the antifreeze in your car. So your car, if you can understand your car heating system, how does it work? You can understand hot water system. You have your radiator outside. You have the engine, which is your heat source, combustion, internal combustion. You have another radiator inside, I think it's a condenser, to pump heat exchanger to pump the hot water into it, and the air from the AC circulate around it. So if you understand that, and you have the thermostat and control air in and so forth. And so the air usually, the radiator fluid, try to get rid of the excess heat through the radiator. As a matter of fact, the heat in your car is the only free thing you get from your car. It's because it's excess, it's unwanted. So heat from the car is amazing because again, it's just being dumped outside. What about non-fluid transfer? Transfer through solids or conduction. Is it possible? Yes?
Yes.
Yeah. You can go and do metallic mesh in the ground and pump heat through that. It does work. It used to happen in the past when they used to put some steel rods into the chimney on the floor to heat the second floor from the bottom chimney. It is possible. There are ways to store heat in concrete, granite, a lot of solids. So you can use heat batteries of storing energy into solid. It's possible. There are places in Germany where they use solid as a heat storage medium. They use blocks of concrete to store heat and distribute fluid through them. So you can use and transfer heat through solids. Also, I've recently seen somebody from, I think, the Boston area. They have a company that they have graphite columns that they stick in the ground, and graphite is a very good conductor, and by doing so, you will absorb heat and temperature from the earth, or pump temperature to the earth, with no need to move fluid. Geothermal through solid, which is really great because the problem with geothermal is you have to keep pumping water or air into the ground. Okay, so what is geothermal? What do you think is the temperature if you go down, if you dig a hole?
Cold.
Huh?
55.
55 all year round. If you go deep 10 yards, which is 30 feet, you get a solid 55. That's amazing. So imagine that you don't have to heat your house from 0 to 55. You get 55 for free. Then you just have to heat from 55 to 75 or 65, which is 10 degrees. That's a really good way to cut on the cost. Yeah.
What's the cost on that to even have something like that?
It depends. Think about it. You have to have a well. You have to have a good network, and it's still very custom made. Last I heard, that was 3 years ago, a system was put in a house for like 30 or 40 grand. Yeah.
That's expensive.
It is, but it gets better. It's getting cheaper. That was 3 years ago. Probably now you can put something for less than that. Probably you can make your own.
Well, gas and
Some way.
electric is
Does,
going up now.
Yeah.
Does like the geological, like, does it
Location
matter
does
where
matter,
your
yeah.
house, does it matter where your house is located?
Exactly. How far you gotta dig? What kind of ground do you have? Is it like rock? Is it not? Because you have to dig a cavity to get that heat exchange. So it does matter, and sometimes it's cheaper than others. And there are some other ways to do it. To think about it. Some people are thinking of using the municipal water as geothermal. It's already dug and deep. But can we circulate that around the house and get some heat out of it? The water comes at 55 or 50 in the depth of the winter, coming out from the municipal water at 55. So we can use that. Eventually, it is possible. It is possible even from colder climate to be combustion free. Between heat pumps and geothermal, we can do it. Geothermal is not really doable for like one house. It's something that has to be done as a block. You get a block, you get a big well investment. It's at the 40,000 will be prorated down to 5,000 a piece. But again, it has to be a capital investment. I know in Germany they have a lot of malls. I talk about Germany a lot because they have a lot of engineering advancement. They have malls completely heated by geothermal. What they do is they have a big kind of storage underneath the mall, as big as the mall, where they heat the water through solar panels in the summertime, and that heat will stay all the way into the winter. So with small subsidies of heat, you can manage to be energy. You don't have to burn any energy. Okay. Again, it takes money to make money, I guess. You know, you have to invest a little bit more. Okay. Infiltration is air exchange. This is how the house breathes. We want that. And we talked about that last semester. Is how much porosity do we need? How much holes do we need? And we said that it's better for us to have control over the air we bring in. Okay? But this became very, very important, and a lot of companies had to go and retrofit their air exchange because of COVID, right? You have to change the air. If we have the right amount of exchange, probably we have more dilution of particles. Transmission is heat transfer through a medium, and this is what the main two heat losses in a house. We talked about that last semester a lot. It was in the final exam. I'm going to keep asking you that. So, infiltration and transmission. Transmission is through the walls, windows, doors, ceiling, and so on. And when we do the heat loss calculation, the first thing we do is we calculate infiltration, and then we calculate transmission. So, let's put something down here. So, total heat lost equal Martha, you see? So Q total equals Q infiltration plus Q transmission. Q infiltration equals somebody?
Area and
No, not area.
volume.
Volume times the filtration rate times temperature difference, right? And you don't have to write it, it's in the book. in the book. You can write down the number somewhere in there. Okay. And yeah, it's in page 27. And heat transmission. Equals area times U factor times delta T, which is this thing here. Temperature inside and outside. Okay? And U factor equal 1 over R, which is the resistance of that material. What else? Anything here doesn't make sense? Volume is length times width times height. Infiltration rate. Where you get that? Book or internet. And that is okay. So we will use that, and if you do temperature inside minus outside, and you get a negative number, that means it's the direction of heat. So it makes sense now in the winter. Are we losing heat or getting heat? Losing heat. And in the summer, we'll gain heat. There is no such thing as coldness, okay? Coldness is the absence of heat. So either you have heat or you don't have heat. You can pull out heat until you get absolute zero. That's what the complete absence of temperature. That's when everything stops, absolute zero. But there's no, you cannot pump in coldness. That's just
It's just heat leaving.
heat leaving. You're just losing heat. Heat is the existence. Okay, heat transmission. You are required, and you need to know the material properties, which means I'm not going to go too deep into it. We just look it up. But the composition of the material makes a difference. There's something called the K factor. The K factor is the material property. Scientists go and measure these things, and they give every material its own K factor. The K factor evolved to something called R, and the R evolved to something called U. For our intended purposes, you have to know is the U factor and the R. When you go and buy insulation, for the layman, they have the R typed on it. This is R4 here. So that's the resistance. And there, depending on the material, there is very good resistance to material. I was telling Nick earlier, wool is very good insulator. It's so thin, but it's very hot. So the resistance, the R value for wool is very high.
Is it because it conducts heat
Less,
from your body, or like can you use that in like?
no, it resists heat transmission. It resists heat going through it. The material itself will resist. And wool is organic. Organic material can have rubber, like rubber, wood, so on, hay. They always are a bad conductor. Any organic material is a bad conductor. So wool is a very bad conductor, which make it a good resistor, right? So we resist heat transmission. There are some thin materials that have really good resistance based on the composition of the material and sometimes the voids in it. So that's one thing. So wool is one of those materials that actually, even though it's so thin, it is very highly resistive to heat transfer. The other thing, there's something called aerogel. Aerogel is the new scientific thing where you have 1 millimeter that can resist 500 degrees on one side, and it'll be cool. You can touch the aerogel, and you have 500 in one side. I think I have a picture of it somewhere, but it's really good resistor. But it's very expensive. It's one $100 for a yard, square yard. So there are some inexpensive material to use for insulation. Heat transfer law, this is the law, and design and outdoor temperature. This is what you need to know. We did that already in the project. We get to know the heat transfer law. We did all the calculations, 3 things you need to know. And then you find the wall, you find it actually conducting a lot of heat. This place really not that good. We're losing a lot of heat. What are you gonna do? Insulation. So we did that also last semester in the project. You have to pick a material. You find the floor and the ceiling are leaking a lot of heat. So, okay, now what? We gotta go and find some good insulation. And it's always better to build things well than to try to go and fix it later. You're gonna open the wall and put some Mickey Mouse job kind of insulation. It's better to have a wall built to be insulated correctly. Because if the wall is already built, what are you gonna do? You have to either take the drywall, stuff things in it, or you can make a hole and pump some loose insulation, which is not going to be that good. So it has to be packed. Okay, so this is an example for insulation requirement. Let me go back a little bit. So how do we calculate for insulation? You did a heat loss calculation and you realize that the room loses 3,240 BTU per hour. Okay, so I'm doing the project, or you're doing your house calculation, and you find, okay, this room is losing a lot of heat. Let's do the example here. This is a floor plan. This is room 1. So this room loses 3,240 BTU per hour. Of course, you did that calculation knowing that temperature outside is less than temperature. That temperature outside was 10 degrees, and the temperature inside is 70. So okay, the room was only has one wall facing the outside, so the room has 2 walls. Okay, screw it up a little bit. Fine. Let's make it this room. This room. One wall facing the outside. Okay. These rooms are all going to be 70, 70, 70. So, Jacob, if this room is 70 and this room is 70, is there any heat transfer around here?
Yeah.
Huh?
No. Equal.
Yeah. There is no heat transfer because this is 0. 70 minus 70 is 0. Anything multiplied by 0 is 0. So there is no heat transfer. In theory, you know, it could be 1 degree or so, but it's just easier to make it, to assume that it's going to be no heat transfer between that or very small. This wall to the outside is 8 by 15. Okay, I'm gonna throw this away. Get another one. 8 by 15. So we got that. And we find the U factor for the wall. Okay, there is no window. The U factor for this equals 0.45. Okay, so the resident says that this is too much heat loss. I want to cut this by half. Is it possible? Okay, we'll see. Let's do the math for this. So what is it? First, I'll have to find. We have the heat loss already, but let's calculate that. We got area. What is 8 times 15?
120.
120 times the U factor 0.45. Times 70 minus 10 is 60. What do we got? Multiply those 3 together. Somebody with a calculator.
What was it again?
120 times 0.45 times 60. How much?
3,240.
Okay. Okay, so the calculation was correct. And what is the resistance that I need to reduce that heat load by half? So first thing I can do is if I have the U factor, U equal 0.45. What is R? Alec? If U is 0.45, how do I calculate R?
Multiply it.
Over 1? Yeah, 1 over 0.45. What do I got?
2.2.
Huh?
2.2 repeating.
Okay, 2.2. Okay, so I know the resistance to the wall is 2.22. Knowing just by right off the bat, if I want to cut this by half, I have to increase the reduce the transmission. So the resistance has to increase by how much? Yeah, the U factor has to increase, right? Yeah. So I have to double the resistance in this case. So I need to add 2.22. You're not gonna be able to do that exactly. So you're gonna get at least R2, add R2 board, and that will make U equal 2.22 plus 2. I added resistance to it, and then I'll have 1 over 4.22. What is the new U? So I went there and I bought a board like this one, but then instead of it being 4, I put 2. So I know that will give me some reduction, not as much. What is 1 over 4.22?
Point two three six nine. So 2 3 7.
2, 3.
Yeah, well, it would round up to 0.24.
Okay, 1, 2, 4. Okay, then I will tell the person I'm dealing with that 120 now times 0.24, which looks almost half the U4, right? Times 60, and probably I'll get something around 1,000.
728.
Huh?
1,728.
Yeah. 700. BTU. That's just by adding 50%. I did some math here.
That's just pretty much to save on the cost of the energy that you use in the house, right?
Yeah.
So when you go, just add more insulation to the house, that would reduce the transmission loss.
Exactly.
I was gonna say, what's the difference between infiltration and transmission system?
Okay. Transmission is through the wall. Infiltration is whatever you're gonna air, you will lose through the cracks of the house.
Okay, so the transmission is what the wall is capable of resisting?
Yes.
And, okay, like,
The infiltration, you have to go and caulk the house and measure how much
yeah, like
infiltration
the
is there.
slips, like if you
Yeah.
have the window open or something?
Yeah,
Okay.
the frames of the window, the sash, and all this kind of molding. Okay, but this we can counteract transmission by adding insulation. We can counteract infiltration by kind of retrofitting those areas. Some of the areas where you lose a lot of heat is sockets, by the way, outlets. There's no insulation behind it, so we want to make sure that it's completely sealed. Windows are sealed. My living room window is leaking air like crazy. I can feel actually, in the cold air, it's windy, I can feel the cold air coming in. So probably I have to go on caulk it. This is the new one. Change the new factor, get the BTU to 50% off. 2.22, when add. You get the idea. You're not gonna have to do that exactly, but at least you can calculate for the new heat loss when you need to. So you did a heat calculation and realized that the room loses 1,500 per hour. The room has only one wall facing the outside, same thing, okay? The inside is 65 and the outside is 10. What insulation value, our value that you need to get heat loss reduced by 80%. Again, some lengthy calculation, we'll go over it. Same one. So the first thing is the 1540 to reduce it by 80%. I give an example of reduction to understand percentage. To understand 80%, I'm gonna multiply that by 0.2, which is 20%. So 304 BTUs is 80% reduction. The reason I'm giving you this percentage is because it gets a little bit confusing when you're trying to go and somebody trying to sell you on something and tell you reduction. Okay, are you increasing the efficiency or are you reducing the cost? So it's really important to have good on this terminology. So I have 80% reduction. So the heat loss is going to be 20% of what it was, which is 300 is 20% of 1540. If you want to think about it another way, think of discounts. When somebody tries to sell you a shirt for $400, and they tell you, okay, I'm going to sell you this this shirt for 20% of its value. How much is the shirt? It's $400.
Sounds like
Yeah, $80. So the same idea of reduction. Whatever works for you, use that for reduction. Okay, then we get the area, we get the U factor, 1 over U, to get the R. And this equation, you'll find it in the last page of the book, and it's also available here. But if you look at page 159, you will find the R insulation equation in case you need it. So, and again, for most quizzes, or it's gonna be open book, I don't expect you to remember this equation, but in case you need to know what is the R insulation, you can look at this one, give you the R insulation, and you plug in the numbers, the new heat loss that you want, the R of the wall that you found, and temperature difference, and the area. After that, it's just check and plug. You remember PEMDAS?
Excuse my gear outside.
Yeah. So you just process this. First you do the multiplication, divide by the Q, then subtract the R wall. It's there. The equation will do some, we'll process this a little bit. Okay, and it's good also to do it step by step on paper. I like to do it this way, so I can see where did I mess up. Especially when I get a very funky number. What would be a funky number if I get something really high, or if you get number in the minus, you just go on trace your steps. So I put the numbers here, and I got, in order for me to reduce the heat loss to 300, I have to add almost R12. Is that reasonable now? That's really, R12 is going to be a lot. Unless I have some scientific material or some for a wall. For the ceiling, it's okay because you can keep pumping stuff. But if this is R4, so it's going to be something really thick. So that doesn't make sense. Unless I'm going to go invest in something really industrial strength insulation material. So that's being said. This is percentage reduction. You can look at it later. Another example. You can go over this when you want at some point. Just look at that math for it. But what I want to say is more insulation always better. So let me go over the math a little bit, just to show you how it's done. You don't have to know that, by the way. It's just for information. It's for entertainment, okay? Thanks to So how do we get that equation? Again, area times U times delta T. How do we get there? Area times 1 over R times delta T. But the resistance is always the total resistance. So area times 1 over R wall plus R insulation. You agree? Times delta T. Now I'm trying to solve for R insulation. So I have to move everything else to the other side. By doing that, I'll do this Q total divided by delta T and divided by area. Okay, gonna flip both of them. Okay, then suddenly put this here in parentheses. No. This is how we came to the R insulation, and if we look at it, this is how we came to it. And so I took an example just to show you why at some point, if we keep increasing the insulation, we'll end up with not significant heat loss reduction. So in this, I guess, made an example. I used this equation and I plotted the heat loss versus the R insulation. So I kept the temperature difference the same. The wall is not going to change size, right? I'm not gonna be able to change the wall. I'm not gonna be able to change the temperature. All I can do is increase insulation. So I did plot all the results by increasing insulation by a magnitude of 0.5, okay? And this is the heat loss. So if you notice, the area is the same. The U keep changing respectfully with the insulation, and the wall is the same. DT is the same. So plotting this, look at that. 1 is still the same. 0.5 reduction, 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 3. Then as we increase, it comes to a point of stagnation. When you keep adding insulation, but the reduction in heat loss is not that much. The magnitude becomes kind of redundant. And if you apply that, so I'm plotting now the insulation, the heat loss versus the insulation. Actually, this is flipped. This is the heat loss, this is the insulation. And you look at the graph here, you see at some point, it just becomes, there is some reduction, but it's so insignificant. It looks like it's going to be stagnant. So you don't have to do any of that, but it's good to know that at some point the insulation you can keep adding, but it's not going to add. And scientifically, the issue is at some point the conduction through the insulation becomes an issue. It's not going to use the heat loss anymore. So you're gonna find a sweet spot where you don't break the bank and have some insulation. So there is no way that you're not going to have any heat loss, but you need to have some kind of insulation. Did I convince you or not yet? You convinced?
So you don't
Okay,
need
you don't. Okay. What you need to remember from all this nonsense here is heat loss through a medium, that's transmission, okay? And we know how to calculate that. Second, the rate of heat transfer is a function of the insulation, which is the R value, and the material. The surface area, more surface area, more heat loss. Temperature difference, more temperature difference, more heat loss. And the reason is we don't spend as much money into cooling in New England than heating is what? Why? The weather. The temperature degrees in the winter is high. So we go all the way to the -8, 17, that's almost 80 degrees. In the summertime, it's only 20 degrees that you cool. I mean, even if you go to Texas when it's 110, you're still cooling only by 25%. That's not that bad if you can really get the heat in the house. Where is the heat going? That's important. Are you losing heat or gaining heat? That is very important. For those who are taking the refrigeration course, when you do the cooling, what else do you have to account for? Are you measuring sensible heat, sensible temperature, or latent heat? So we have to accommodate for latent heat, and that depends on the area. So you have to go and accommodate for that, especially if you live in a wet area like Florida. So you have to always counteract humidity. Okay? How to calculate required insulation? I showed you how. There's also always a sweet spot for that, and it makes a difference, and that's why last time I checked the DOT and the insulation for the roof, the requirements are 30 for ceiling. 30 for ceiling, it makes a lot of sense. It's gonna be this much. You're gonna do a lot, or they have to have some condensed foam, and it's very required because you have a lot of surface area, and you have a lot of heat coming to the ceiling. Okay, is more insulation always better? No. Cost of insulation versus heat loss, is it going to be worth it or not? Okay, check the blackboard. I'm gonna put some, there's homework, I'll put some videos. There's a video of me going over this PowerPoint as well, if you have any questions. Next week, what did we say? What are you gonna bring with you? Computer, floor plan. If not, I'm gonna have a floor plan with me, and we'll do a quick lecture like that, and we'll sit together and start crunching numbers. Calculator, and I'll work with you. I'll explain it first, so and have it work, and we'll go around and answer questions. I want you to use the Excel sheet because it makes things a little bit easier. It does the math for you, you just plug in the numbers, and it should just come up. And it will be a good tool also to show you how to change that from heating to cooling. So we'll do heating and cooling. Okay, that's all. Thank you.